Greetings and welcome. Today, in our preview of calculus, we're going to talk about area under a curve. Okay? Area under a curve. And it turns out that this area is solved using something called integrals. Integrals is what they'll be called, but we'll talk a little bit more about those later. So this is the premise. So suppose I have some function, right, something like that, and I want to find the area of this region between point A and point B under that curve. All right, and this would clearly be a valuable thing to know. If you were working with solids at some point in three-dimensional calculus, you would take this area and then rotate it around a point in 3 dimensions and then get like a donut-shaped thing that's got like a volume with this curve as part of it. You can do all sorts of crazy things with it. But that's what we're going to be looking for. So how could we find the area underneath that curve? Craziness. And it turns out there's some interesting results. Riemann sums are one of the ways these have been done. What if I divide this space into even portions? So let's see. Here's, I've cut it into 4 parts. And imagine that I find the height of each of these bars. All of these bars are the same width. Let's see. And I could find the area of all of these bars, right? So here's A, here's B. I think we end up calling this point x sub 1, x sub 2, x sub 3, and B can also be referred to as x sub n, lowercase n, I suppose. All right? And what would these heights be evaluated at if this function is f of x? What would the height of this leftmost bar be?
The value of y when x is equal to...
Right? Yeah, the value of y when x is equal to x sub n, or b. So this would be f of x sub n. This would be f of x sub 3 in this case. Right? So all I'd have to do is plug in those numbers. Actually, this one is, did I do that backwards? X sub 2, did I? Let's see. Let me erase them just a moment here. Yeah, x sub n definitely. X sub 3 would be this point, so this bar is x sub 3, f of x sub 3, yeah. Then x sub 2 is this height, so that bar is in fact f of x sub 2. All right? And this bar is x sub 1 high, yeah, so f of x sub 1. And it turns out this would actually, if I added up all of the areas of these rectangles, I would have an approximation of the area under that curve. Now would this...
Not a very close one.
Yeah, not a very close one. Would this be an overestimate or an underestimate?
Overestimate. Far over.
Yeah, it'd be an overestimate for sure, because you can see there's this little area here that's too much, and this little area here that's too much, and this little area here. This is actually called a right-hand side Riemann sum. I don't know if I even have Riemann here, but that's okay. The guy's name is spelled like R-E-I-M-A-N-N or something to that effect, but I'm not too worried about that right now. But this is calculated from the right-hand side.
The more boxes you have, the more accurate.
But yes, precisely. If I was able to divide this up into more boxes, all right, where the difference between my x values, all right, actually let me label that maybe with yellow. So suppose this distance is called delta x, right, the distance between my x values. If that distance got smaller and smaller, all right, or if n got greater and greater, all right, where I had, say an infinite number of rectangles representing this area, or the value of n would approach infinity, that I would get more and more accurate results. Right? Would that make sense? So what I'm looking at is finding the area. So I would have to take the limit as n goes to infinity, so the number of bars goes to infinity, right, of the sum of those bars. Okay, so there's going to be a limit, and there's going to be a sigma in this formula. Okay, but does that kind of make sense? Sigma, I'm going to be adding up all the areas of these bars. Let's see, actually, what would the area of one of these bars be? What would the area of this bar be? The height.
Delta x, y.
F of x and
It'd be delta x is the width of the bar, and I'd multiply by,
Y. F of x.
right, the f of x,
N.
right, sub n. Or, well, that would be the area of this bar. Or this one would be delta x times f of x sub 3, right? Or delta x times f of x sub 2. So actually, one of the things we might be able to do is just call it x sub I, where I is whichever bar we're on. Okay? So that would represent...
F of x sub n.
Yeah, for that specific one, I would equal n. But for this one, I would equal 3. For this one, I would equal 2. For this one, I would equal 1.
Mr. Rod, wouldn't x sub n just represent all of them? And you use n.
You know,
Well,
F
x sub n would
Or
give
you're saying
me...
that x sub n is only the last one.
X sub n is only the last one, yeah. Yes, I think. So yeah, so x sub n would just be the height of the last value. So that's what I'd want to be able to calculate
wow, this is
all of those independently, which would be good. Let's see. I know where to go. Intermission. Now, it turns out that I also can calculate a Riemann sum using a left-hand side value. And if I did a left-hand side Riemann sum, would you suspect that, yeah, in this case, it would be an underestimate, right? Why would it be an underestimate? Right, because that would be, all the bars would be kind of these yellow ones, and I'd be missing this portion of the triangle. All right? Some people actually will take the average of both of those. All right, it's also sometimes people will do a midpoint Riemann sum,
That's not accurate.
and different things like that, where, I mean, you've got kind of this piece cancels out with this piece-ish.
Not really.
Not entirely, depending on how the curve is. I mean, if it was a straight line, that'd be fine. But not quite. So this is the idea. If the number of rectangles goes to infinity, and I find the sum of all the rectangles, that would represent the area of the curve. Okay, so let's maybe draw out a rough idea of what that would look like. So we're saying that we want to find the sum of all of these, right? So how would you represent that? That would be sigma. Actually, maybe I'll write this in green. So the sum of those rectangles, we would have I equals 1 to n, right? So that way I'm plugging in x sub I, x sub 2, x sub 1, x sub 2, x sub 3, all the way to x sub n. And I would multiply this, and I think your book actually writes the y value first. So f of x sub I times delta x, right, is the idea. And delta x, we'll actually end up being able to calculate that a little bit later. But that would just be the width of each of these bars. Actually, how could we find delta x? Well, we'll come back to that in a minute. So this represents the sum of all of the bars. All right. Now, if n is 4, then that's the sum of 4 bars. If n is 10, that's the sum of 10 bars breaking up that space. But I want n to approach infinity, so how could I represent that? Yeah, I'll throw a limit in front of this. So the limit as n goes to infinity of the sum of all of these rectangles. All right? So it's the limit of a sigma. And this is actually, this formula is referred to as a definite integral, is what it ends up being. And it turns out, instead of writing the limit as n approaches infinity of the sum as I goes from 1 to n of f of x sub I times delta x, they actually have a symbol to denote this.
Wait, wouldn't it be limit as delta x approaches 0, to...
Yep, that's another way you could think about it, because the width of these bars is going to be going to 0 as n goes to infinity. Actually, maybe let's ask that question. How could I find the width of these bars? They're all evenly spaced. Okay? How could you find delta x? What are your thoughts on delta x?
B minus A over N.
Okay, so this whole width would be b minus a. And I would divide that by however many bars there are, right? Does that make sense?
N.
So dividing by n. So we had a student just say a moment ago that delta x should be going to 0. If n goes to infinity for this expression, is delta x going to 0?
Yes.
Yes.
Because b minus a is a fixed value. That's a fixed distance, because I would say I want to know the area under the curve from 1 to 5, or from 0 to 7, right? Or something like that. So that's a fixed value, and I'm dividing by a number that's approaching infinity. So yeah, this would be going to 0, which verifies what you had said earlier. So they defined it in terms of n going to infinity. I don't know. I think it would be harder to define it the other way. Having the limit as delta x goes to 0. Because our other values may not be as friendly for that format. But yeah, so it turns out this is a little formula for delta x, which is nice. And it turns out we'll actually end up having a formula for x sub I as well in a moment. But first of all, before we do that, I want to show you this notation. So the way that we write this, let's add a new symbol for it. And I think one of you guys who did the wrong homework the other day ended up learning a little bit of this. It is the definite integral from a to b of f of x dx.
Wait, what's that?
So this is a definite integral. Is the definition of this.
What's dx?
Dx actually is another way of saying kind of delta x.
So I can just see with the
It's
triangle?
actually related to the derivative of the function with respect to x is kind of what that means. But yeah, so that's maybe one thing you'll learn about calculus is there's a lot of notation, right? Just getting used to some of these symbols, right? So if I wanted the definite integral of 0 to 10 of a function, dx, I would be talking about finding the area under the curve of that function from 0 to 10. And actually what's interesting, I believe if say that function happened to go beneath the y-axis, that it can account for that with a negative area. Or if within that region, if parts of it are above and parts of it are below, ouch, my elbow, that it would have like a negative area added together with some of the positive areas and stuff like that. But preferably you try to avoid some of that when possible. So that's what, like, with something like this, we could actually end up, finding the area of an ellipse, right? If I have an ellipse set at the origin and I had an equation that just represented the top half of that ellipse, you could find the area from endpoint to endpoint, and you could actually find that formula. And then that's what's interesting about calculus as well, is that using this, then patterns would emerge for particular shapes or curves that then you could find more easily usable generalizations or formulas representing those areas. So we could actually, I think at some point, maybe even find a formula for like the area under a regularly shaped parabola or something like that. So you could have like actually the area under an arch if that arch was a parabola, if you knew the height of the arch and the width of the base. So you could actually develop your own area formulas using calculus. So that way, not everyone would have to do the calculus to find the area. You would just say, here's a formula for this particular shape. It works every time, right? And then all would be well in the world. So let's see. What about x sub I? Well, let's rewrite x sub 1. Maybe I'll zoom in on that. I think that's what I'll do. So here is my let's see. So this is from A to B, right? A to B. And let's divvy this up. So I'll divide it in half, in half, in half. That might be enough to recognize a pattern. So this is just kind of like looking at the bottom part of that. So here's x1, x2, x3, right? And b is the same as xn in this case, right? Or whatever. And the distances between these are delta x's, right? So delta x, delta x, delta x, delta x. So let's.
I keep calling delta as a.
Yep. Just a little triangle. Little delta. Delta means difference. So delta x is actually talking about the difference between x1 minus a, or x2 minus x1. So it's a width or a distance that we're referring to here. So what's a way I could write x1 in terms of a? It's the same as a plus what? A plus a delta x would give me this new x1 value, right? So a plus a single delta x. What's a way I could rewrite x2 in terms of a? A plus, right, 2 delta x's, right? 2 delta x. How about x sub 3? X sub 3 would be a plus 3 delta x. Man, I'm going to have to teach my son to count like 1 delta x, 2 delta x. Like, that'd be great. He'd sound so smart.
X sub n equals a plus n delta x.
So what's our formula for x sub I?
X sub I equals a plus I delta x.
Right, so this was 1, 2, 3, and conveniently those 1s, 2s, and 3s corresponded with the 1, 2, and 3 there. So it'll be I, let's see, that's a times delta x. And this I is not I, the imaginary number. This is I as in the index of summation from that sigma notation. And that rhymed a little bit. I'm kind of happy with that rhyming.
I delta x sounds kind of like I Robot.
Yeah.
You know, like what if there was a movie where the delta x's rebelled and tried to wipe out all the regular x's, but one of the delta x's rebelled against the rebellion?
I suppose so. I could see that. So we've got a formula for delta x, and we need to know what delta x is in order to figure out this one to find x sub I, right? Because delta x is within that. And once I know delta x and x sub I could then plug in for here and here because I already know the function, and then I would just plug in my x sub I, right, into the function. And once I have all that, then I'll be able to actually calculate this area. Okay? So we might get one problem done in this video. We'll see. But then we'll have time for some classwork, party work, so that'll be good. All right, so let's see what we've got. Oh, actually, one more thing. There's a whole bunch of factoring facts that we'll need to know in order to do this. Things that we've never learned shorthand. That you call that focused? Come on, camera. Come on, camera. These are found, as you can see, on page 962 of your text. So I'm going to snapshot these into my notes. You would be allowed to have these on a quiz or a test. I don't need you to memorize them.
Should I write those down?
You don't necessarily need to write them down. Just write that some factoring patterns are found on page 962. Factoring. Rules or patterns, I don't know what you want to call them. On page 962. All right, just so that way you have them, because during our work, we'll end up getting an expression like this, And in order to evaluate, we'll actually have to rewrite it in that form. And yeah, I don't think you'd necessarily spot or know all of these. Yeah, I mean, some of them I think we might have been able, well, yeah, these are like weird little factored versions of those expansions. At least those are finite series. Theirs aren't, well, actually in our case, n is approaching infinity, so weird stuff. But anyways, so we'll end up using those as well. All right, let's see. I think I'm going to try to fit one in here. Okay, here we go. Let's do an example. One example. Exemple. So suppose, use the limits and the area of the region between the graph of y equals x squared and the x-axis from 0 to 1. Okay, so I'm looking for this. Find the definite integral from 0 to 1 of x squared dx.
And,
so graphically what that means, I'll draw a little picture over here. Yep. That's good. So my function is x squared. All right, so here's f of x equals x squared. And I'm looking for the area of this function between 0 and 1. So I'm looking for the area of this region. Well, yeah, I guess that'll do.
It's a very exaggerated.
Yeah, it's definitely not to scale. So I'm looking for this area, and the way we're going to do that is dividing it up into rectangles, such that the number of those rectangles approach infinity. We'll find the area of each of those rectangles and add them all together. All right? Easily done.
The area of the rectangles that are approaching 0.
So, what does this...
Many of them.
So I just want to point out, f of x is just the x squared part. The dx is just part of the notation tacked onto that. So don't ever get thrown off by this dx, all right? So if I had like x squared plus 1 or something, the dx would be after that and is not part of the function, okay? But this is what we're looking for, area under that curve, right? So what does this represent? This represents the limit as n goes to infinity of the sum as I goes from 1 to n
wait, hang on. I
Yep.
can't keep up.
of f of x I times delta x. So the first thing we should do is let's find out what is delta x. Does anyone remember the formula for delta x? It was
A minus B over B minus A over N.
b minus a over n. And then we'll find x of I, which was what? A plus I times delta x, right? I believe. So let's figure out what both of these are in this case first. So over here, delta x. So this would be my step 1 and step 2 if you wanted. So what is delta x in this case? Let's see. B is 1, A is 0, and I'm dividing by n. So that is 1 over n. It's delta x. So what is x sub I? A is 0.
A is the one on the bottom and B is the one on the top.
Yeah, A is to the left and B is to the right. So this is A, this is B. All those, yep. I is still in terms of I, and delta x we just found is 1 over n. So what does x sub I simplify to become?
1 over N.
Yep, or we'll just write it as I over n. But yep, 1 over n I is the same difference. So here's our x sub I. So now I can plug these in for here and here. So f of x is x squared, so I'm actually going to plug this in to the x squared part there, 4x. All right, and that represents plugging in the x value to find the height of each of these rectangles. Okay, that's what we're doing. All right, so trying to keep in mind the big picture going on here. We got this, guys. This is like the last trickiest thing we'll do. Actually, the next lesson we end up doing is easier than this one. So this is going to be the limit as n goes to infinity of the sum of I equals 1 to n of. So this will be I over n squared, right? F of x sub I. Function f was x squared, and I'm plugging in 1 over n, multiplied by 1 over n, right? Because delta x was 1 over n. So lots of substitution stuff going on here. If you want, I could actually do this, and this, and this, right? So that's what's going on. So let's simplify this, shall we? So this is, and I apologize for all these limit sigmas. Maybe we can just write lime. So that's I squared over n squared times 1 over n, right?
Hang on.
Which would be limit of the sum of I squared over n cubed, if I'm not mistaken.
Versus 1 over n.
What do you mean 1?
It's not imaginary numbers.
Well,
Yeah.
no, I is approaching 1. I equals 1.
No, I starts at 1 and then cycles through all of the n's. So let's actually deal with the sigma first. So I equals 1 to n. That's what, there's just so many variables you have to keep track of. So this is the same as the limit as n goes to infinity of, let's actually write this out. So when I is 1, this would have been 1 over n cubed, right? When I is 2, this would have been 2 squared. Actually, maybe I'll still write that out. 2 squared over
Oh man, I can't.
n cubed.
Oh, and then this is where we use that substitution.
Yeah. And then when I is 3, it would have been that plus, and it cycles all the way through to n squared, not infinity yet because I haven't done the limit, n squared over n cubed. Right? So that's what the sigma meant.
So I
Can we agree?
is going from 1 to n, and n is approaching infinity.
Yes.
So I is approaching
The last I is approaching infinity. I is incremental by 1, right? Whereas n is kind of on a gradient.
Everything.
Yeah. Okay. So it turns out I can actually factor out a common thing from all of these. What do every one of these terms have in common that I could factor out from them? The n cubed. So I can actually factor out a 1 over n cubed from all of those, and I'd be left with 1 squared plus 2 squared plus dot 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 all the way to n squared. Right?
Which is
Come in.
n plus 1 times 2 n plus
Or was that a
1.
separate note? No problem. When I'm at home, if there's any knocking noise, my dog just starts barking, regardless if there's someone at the door or not. We're trying to desensitize her just a little bit. So like
Anyone
sometimes
knocks
we'll
at
intentionally
the door, there are no for God will start howling. No matter who it is.
That's a good one.
Yeah. So this portion right here, this is why I gave you that little other alternative shortcut. Which one does that match up to?
N times n plus 1 times 2 n plus 1.
This guy, the second one, right? So let's see. I don't have that memorized. N times n plus 1, 2n plus 1, all over 6. So this is the same as the limit as n goes to infinity of 1 over n cubed
Oh my god.
times n plus 1 times 2n plus 1
My god.
All over 6.
all over 6.
All over n cubed.
Well, or I've got the 1 over n cubed on the outside there.
Or 6 n cubed.
I'm going to have us take a shortcut here. So if I multiply all of these out, I would probably distribute n into that, and I'd have n squared. Actually, maybe I'll just shorthand it here. So this is n squared plus n, right, when I multiply the first two. And then I'd multiply that by the 2n plus 1. So I'll have to FOIL it. So what's my numerator going to be? I'll have n squared times 2n is 2n cubed. N squared times 1
2n
is
cubed.
n squared plus another 2n squared, so that's plus 3n squared. And then the last term is n times 1, which is plus n, right? All over 6n cubed?
Yep.
Did we do that right?
Or all over 6. All over n cubed.
Actually, wait.
Which is the same thing. Because it would
Yeah.
be the same as multiplying by 1.
Actually, yeah, that would have been smarter of me. I could have partially canceled this n with one of those right off the bat.
Well,
So-
you can do it right now.
Yeah, we'll do it now. I'm going to write this over here because I think I'm running out of room. We're close. We're so close. So this is 2n squared plus 3n plus 1 all over 6n squared. Okay, so how do I take that limit? What's the trick? Divide each term by n squared, right?
6n squared. Or no.
No, we can leave the 6.
Oh my god, I can only write it one.
Yeah, this is why we're only doing one example today, people. So divide each term by n squared. So I'll have, that will be 2 plus 3 over n plus 1 over n squared all over 6n squared divided by n squared is just 6. Equals 2/6 or 1/3.
About.
Exactly, actually.
Or what about those 2 infinitesimals?
Because as I took the limit as n goes to 0, that went to 0, that went to 0. Right?
But you said that we can't. Because there are certain places where we can't actually write them off.
Well, when I take the limit,
Close to 0,
it-
but they aren't actually 0.
but for limits, it's equal to the thing. It's equal to the thing that it's approaching. So I agree that for really big values of n, 3 over n is just a really small number. But when I take a limit, the assumption with the limit is that it is just straight up equal to the number that it's approaching. And that's why when we had limits earlier, it was just all it had to do with that value was pass the part 2 of the continuity test, because the fact that they were approaching that was good enough for a limit. All right.
Secant lines.
Yeah. So what does this mean? This means the area between 0 and 1 under this parabola was 1/3 units.
Between 0 and 1.
So if this was like 0 and 1 mile, this is 1/3 of a square mile. Okay? Something weird like that. But it's area is the idea. So this area is 1/3. 1/3 units squared. I won't write u squared, actually. Because then that will look like it's a u substitution problem. We've got enough variables in this, I think. So, lots of stuff going on.
2-minute break.
Yeah, we'll do that. We'll do that. But that's the idea. I'm adding up the areas of infinitely many rectangles. Okay, internet friends? That'll do.